All right, hello. So this is going to be sort of the last algebra video that I make in a while, uh, because I'm going to do some other things, I think. Um, I'll decide what that is later. But I think sort of to end off this like series of algebra things, I should talk about the isomorphism theorems, which I guess are the most important theorems in algebra, in my opinion, I guess. So that it basically tells you some things about just like basic isomorphisms that come up all the time. I'm going to split it into, there's four of these, there's four different isomorphism theorems, and I'm going to split it into four videos because otherwise it'll be really long. And I'm only going to do it for modules, again, because otherwise it'll be really long. So before we even start, we need to recall a couple of things. So first, recall that the definition of a module. So if we have a ring R, we can form modules, left R modules over the ring. And those are the structures where you have scalar multiplication by elements of R and addition of the module elements themselves. And then if I have two of these R modules, a module homomorphism between them is a function between them such that it respects the structures, namely the scalar multiplication and the addition. So it means that right, f of m plus n is f of m plus f of n for any two elements m and n of the module m. Oh, maybe I should call them m and m prime because they're both elements of m. Okay, so that's respecting addition, and it also has to respect this scalar multiplication by elements of the ring. Like that. And then when you have an R module homomorphism, you get these kind of canonical submodules. One of them is the kernel of the homomorphism, and the kernel is all of the elements that get sent to zero. So it's all of the m in the domain that get sent to zero by f. And it's a submodule of m because it consists of elements of m that get sent to zero. And then we also have the image of f, and the image of f was all of the it was like the range of the function. It's all of the elements of the form f of something where m is in m. So it's everything that the function hits. And it's a submodule of the codomain. And given any submodule, we can form the quotient module. So remember, a submodule is just a subset that's closed under the addition and the scalar multiplication. And then we can form the quotient, and the quotient consists of these cosets that look like this. There's some element of m plus the submodule. And then we have it, the quotient module is a module, and the module structure on it is like if I have two cosets, like little m plus s and little n plus s, you can add those two cosets, and the way I add them is I just add the elements in the module and take the coset of that. And then similarly, if I have a ring element, I can multiply it by this coset, and I just do the scalar multiplication of R by elements of M, and I take the coset. So that's the module structure on the quotient module. I'm sure there are more things we'll need to recall since I haven't done a video in a while, but let's just jump right into it. So there's some recalls. Let's do the first isomorphism theorem. So the first isomorphism theorem says that if I have a R module homomorphism, and let's say it's a left R module homomorphism, then m divided by the kernel of f is isomorphic to the image of f. And this side makes sense because, right, the kernel of f is a submodule of m, so I can form this quotient. So that's the theorem. Let's prove the theorem. So how could we show an isomorphism between these two R modules? And we should recall that. So what is an isomorphism? An isomorphism is an R module homomorphism is also a bijection. And a bijection is something that's onto and it's one-to-one. So the elements of our proof will need to be one thing we will need to do is show that well, okay, so first let me define the map. Let me define the map that we're going to use. I need to define an R module homomorphism from the left-hand side to the right-hand side. So I'm going to define, ooh, I hope my pen doesn't start lagging now. I'm going to define a map I'm going to call F bar. And it's going to go from the left-hand side, M divided by the kernel of F, to the right-hand side, image of F. And I'm going to make this map by taking, right, F bar is going to take a coset, M plus kernel of F. That's what the elements of that quotient module look like. And I'm going to send it to F of little m. And I think to abbreviate my notation, I'm going to say, just as a matter of notation, so I don't have to write M plus kernel of F every time. I'm going to write this equivalence class. Remember, a coset is an equivalence class. I'm going to write it as just like this M in brackets and call it the class of M. So the map will take it'll take the equivalence class of M, and F bar will map it to F of M, which is something in the image of F, right? And then this is a coset of the kernel of F, and on the right-hand side, there's something in the image of F. So this map makes sense. So what do I need to show? First thing I need to show is that this actually is a function. And the reason I need to show that it's a function and that's not obvious is that on the left-hand side, I have a quotient. And whenever I am defining a map out of a quotient space, I need to show that it doesn't depend on the representative of the equivalence class that I pick, because the elements of this are equivalence classes. So I need to pick two different representatives of the equivalence class and make sure they map to the same place to show that it's a function. So I'm going to call that showing that F bar is well defined. So that's one thing we need to do. I'm gonna sketch the proof before I actually do it. Then I will need to show that F bar is in fact an R module homomorphism, because I want to show it's an R module isomorphism. So first I have to show it's actually a map of the correct type. And then I need to show that it's onto, meaning it's surjective, and I need to show that it's bijective. So I need to show that's I already showed it's onto, then I'll show it's one-to-one or injective. That'll show that it's bijective because it's both one-to-one and onto, and then we'll be done. Okay, so how do I show that F bar is well defined? Well, I need to pick I need to take the same equivalence class and pick two different things in that equivalence class, and then show that they map to the same thing. Because in order for something to be a function, I have to have that the same element maps to the same, can't map to two different things. So suppose the class of M equals the class of N. And where M and N are both elements of M. And this class means coset with respect to the kernel of F. In our quotient modules video, I said this means that their difference, right? For two cosets to be the same, it means their difference lies in that submodule. So that means that M minus N is in the kernel of F. That's what it means for those two equivalence classes to be the same. And I need to show that F bar applied to the class of M equals F bar of the class of N. Okay, but if M minus N is in the kernel of F, then I can take F bar of the class of M, and by the definition of what this does is it gives me F of M. So this is F of M. but then m is the same as m minus n plus n. I'm just adding 0 there. So this is the same as f of m minus n plus n, because minus n plus n is 0, and m plus 0 is m. And then because f was already an R module homomorphism, that was one of the assumptions, right? F was an R module homomorphism. So it respects this addition. So f of m minus n plus n is f of m minus n plus f of n. Can break it up like that. And then m minus n was in the kernel of f, so f of m minus n is 0. And then I have f of n here. And then 0 plus f of n equals f bar of the class of n. And that's what I wanted to show. I wanted to show that f bar of those two elements is the same. So I did. I checked that it's well defined. Done. Okay. Next, we need to show that f bar is actually a homomorphism. So I need to check that it respects addition first. So if I take f bar of the class of m plus the class of n, say, because of the way that cosets add, right? This is f bar of the class of m plus n. That's using this, but using the different notation. So I'm just adding the two cosets. That means just add the representatives and then take the coset. And then by the definition of what f bar does, this is f of m plus n. But then again, f was already a module homomorphism. So this is f of m plus f of n. And then f of m is f bar applied to the class of m. And then this was f bar applied to the class of n. So that shows that it respects addition. And then if I take f bar of a ring element r times m, then this is f bar of the coset of rm. Again, by the way the module structure on the quotient works. And this is f of rn, which is f bar. Oh, wait, sorry. Then I have to use the fact that f is an R module homomorphism. So this is R times f of m. And that's R times f bar of the class of m. So I've shown that f bar is an R module homomorphism now. Done. Now I need to show that it's a bijective, one of these. So I'll show that f bar is onto. How do I show a map is onto? Well, I pick something in the codomain and show that it was in the image. So pick any, say y in the codomain, which is the image, the codomain of this map is the image of f. So that, right, if y is in the image of f, that means y equals f of m for some m. But then I know something that maps to f of m. I know that f bar of the equivalence class, or the coset of m, maps to that. So then if I take f bar of the equivalence class of m, or the coset of m, or m plus kernel of f, that equals f of m, which equals y. So I found a thing that maps to y under f bar. So f bar is surjective. Everything in the codomain is actually something in the image of f bar. And then we'll show it's one-to-one. And remember, one-to-one means no two elements in the domain map to the same element in the codomain. So I need to pick, I'll pick two elements in the, I'll pick two, I'll suppose that f bar of something equals f bar of something else, and I'll show that those two things have to be equal so that I don't have like two things going to the same thing. So I'm going to suppose that f bar of the class of M equals f bar of the class of N. And then I want to show that the class of M equals the class of N. Okay, well, if I suppose this, then that implies, right, if I just apply the map f bar, that means that f of M equals f of N. And we don't know that f is one-to-one or anything, but we do know that if I take f of M minus f of N, then that should be the zero element. And then f is a R module homomorphism. That's pretty much like the only thing we're going to use throughout the whole proof. So I know that f of M minus N equals 0, which means that M minus N is in the kernel of f. And then if M minus N is in the kernel of f, that's the definition of what it means for two cosets to be the same. That implies that the coset of M is equal to the coset of N. So that's done. We checked that it's one-to-one. So therefore, we showed that f bar from M mod the kernel of f to the image of f is an isomorphism of R modules. And that's what we were trying to do. Okay, so I'm gonna stop and start again for the next video.